Thank you, Norwin, and thank you everyone attending to this webinar and showing your interest in this very important topic of airtightness in practice. So my name is Markus Diel. I work at the German Aerospace Center in Cologne, Germany. And today I'm going to tell you a little bit about our research with acoustic leak detection in building envelopes. And yeah, let's get right into it. Why do we use acoustic instead of the normal established methods? Well, I guess everybody has happened to have it happen to him at one point or another that when they wanted to open the window in the summer, they were bothered by the ambient noise across the street. So we saw the potential that sounds also travel the same way that air leaks does. And of course, there are already some commercial applications for acoustic leak detection, but a lot of them, or actually all of them, still require manual scanning. And that is why we, on the other hand, wanted to improve on that. And by putting a loudspeaker inside of a house, we said we don't want to scan with a microphone from the outside. No, we used a microphone array, so a so-called acoustic camera, to scan a large area from the outside, and therefore completely eliminate the need for a scanning method. This method, compared to things like thermography or fog methods, has some advantages. For example, it does not need any pressure or temperature difference. And as I already mentioned, we are able to scan large areas at once and don't need any manual search, which therefore can save time drastically. We already did some field tests before we started our big research project, but if you're interested in that, you can look it up afterwards. But I wanted to give a little bit of information about these measurements because it shows quite good how this method works. So when we did some measurements on office buildings a few years back, we had no prior information whatsoever about the building, so we just started to film from the outside and have the loudspeaker in the inside. And then after we looked at our photos, our acoustic maps, that's what you call the finished photo with the sound pressure level on top of it. Then we looked into it and saw, okay, for example, down there in this window, we were able to see something on our acoustic map. And when we had a closer look, we saw, yeah, there is indeed a rivet hole in the window frame. And when we, for example, had a look at a different frequency range, you can see here we have 4 kilohertz, and here we have 8 kilohertz. Suddenly, a new potential leak appeared on our picture. And when we looked at this, we were able to see that there was, in fact, a cable penetration. And we were able to verify that it's not only penetration, but an actual leak by using the established smoke stick method. But however, you can also see that there is some sound peaks right on the glass pane. And of course, that does not make any sense for it to be any kind of leakage. And you can see there are signals still in our acoustic map that are due to any kind of reflection or vibration. And therefore, we saw a huge potential in some research. And yeah, that's exactly what we did. We did lab and field tests, and I'm going to start with some of our findings from our lab tests. So we constructed a new test bench for this. We called it Atlas, which is short for Adaptable Testing Laboratory for Air Sealing. And as you can see on the front side of this Atlas test bench, we have the potential to change different samples or specimen to look at different kind of leakages. In this example, we have the standard big one, but in the small one, we have a glass installed. And we are also able, due to this measuring fan, to measure the airflow rates for the different leaks that we test. And yeah, as you can see through the window, in the inside, we can put a loudspeaker, but also things like heaters or people searching with a fog machine. And on the outside, we have the acoustic camera and, for example, an infrared camera to not only look at the leakages with our method, but also control them with more established methods. I'm going to start with some of our research from the lab. Here today I'm going to concentrate on potential limits. So what are the most complex leakages, or some of the most complex leakages that are still where we are still able to find them with our method. And we're going to do this with two systems, so to say. The first one is the labyrinth system. With this system, we can create various flat paths, and those paths can be varied by changing, for example, the hole diameters of the inlet and the outlet. Here you can see, for example, the inlet hole and the outlet hole are both 5 millimeters. The inlet hole is drilled into this wooden base plate with also those grooves where the seal can be placed into, so that we can create a path looking like this. And therefore, we are also able to change the length of the path and also the number of turns or bends it takes. And here on the top, you can already see one example for a path we can create with this system. In this case, the inlet and the outlet are both 5 millimeters, and we were able to detect this leakage with our method. I also included the Q50 value for each of these leakages, just to give you a sense for the airflow rate. The next example down there, there is a more complex path, or maybe not complex, but at least longer. We have now a 3 millimeter inlet hole diameter and 7 millimeters at the outlet, and you can see we go way longer in both times. And then using the same outlet and inlet hole, we created an even more difficult path, now with 2 bends and a whole distance of around 50 centimeters, so half a meter. And we were still able to detect this leakage with our method, but if we extended the path a little bit longer, then we, for example, here in this case, came to one of our first limits with the method. But of course, in practice, not every leak is guided in a way looking like this. There are also sometimes cavities in between the inlet and the outlet hole, and that is why we construct the second system, which is the so-called sandwich system. Here we have 4 quadrants, and in each of those quadrants, different leakage paths can be created. And if we have a look closer at one of them, you can see we have 3 slits with a given thickness, and then we have an entry. And when we follow the blue arrow, we can see the path, the sound, and the air takes. I also have the view from the side to make it maybe a little bit easier to understand. So we have here the inlet, then the sound and the air goes through this big cavity, through another slit, and then all the way up again, upstairs, up to this outlet. And as an example, or when we did this with a 7 millimeter thick slit, we were able to find the leakage with our method. The same goes for 3 millimeters. So again, we search for a potential limit in our method, and that is why we added another layer on top. This time the outlet was right on top of the previous outlet, but you can see there's a whole cavity now where the sound can be trapped, or the air. But in the 7 millimeter case, it was still possible to detect this leakage. But we found our first limit, so to say, for the 3 millimeters. And when we made it even more complex, so we shut down this outlet hole and opened this one, that was also then at this point a limit for our current setup in the laboratory. So that's it for the lab work. And then we go to the field tests. In the field tests, I want to talk a lot about what difference it makes, which different options you choose when analyzing your acoustic maps, and also how big of a difference different or various sound sources make. That is why we are concentrating on two of them today. So the first one is a low frequency sound source that emits white noise from 90 Hertz to 9 kilohertz. This is this loudspeaker. He has about the size of a volleyball. And then compare this a little bit to the acoustic maps we get from a high frequency sound source, also called a tweeter. And he emits a linear frequency sweep from 10 to 22 kilohertz. And we're going to have a look at two examples here on the field. Both happened at the same construction site of a building that was originally built in the 1950s. So in the first example, we set up the sound sources in the attic and filmed from down below. So we had about a measurement difference of approximately 15 meters. And maybe you can already see it here. There along the eaves edge, there was a small continuous gap. And this is a perspective from the acoustic camera. And when we evaluate with the low frequency sound source, we can see that there is a very wide area over the eaves. So then when we compare this setup with the setup or with the high frequency sound source, you can already see some advantages both sources can have. So for the low frequency sound source, we can see that a large area can be covered. But for the high frequency sound source, we can only cover a quite or a relatively small area. But still, on the contrast, we can locate the leaks with way greater precision. And that is due to the strong directivity high-frequency sound waves have. So the key message you can take away from this is that the results do definitely depend on the speaker's frequency. The second example I want to have a look at is this window, also from the same building. This is the view from the inside, and with traditional methods, like I think we used a fog machine and an anemometer, we were able to find two different leaks. So the first one was at the top hinge of this window. On the second one, we didn't completely need any traditional methods because there was a drill hole due to the constructions happening there. And it was quite obvious, and you were able to see that there was just a hole between the inside and the outside. And this is then what it looks from the outside. So that's the view with the acoustic camera. And when we have a look at different perspectives, looking at this picture, so for example, here we began with the high frequency tweeter. And as you can see from the outside, at least in this perspective, only the leakage at the top hinge was visible. But if we change the perspective a little bit, you can see that the large hole is clearly visible, but on the other side, the hinge is only faintly visible. So what can we take away from this? That our results do depend on the perspective we choose, and that's especially true when it comes to high frequency due to their directivity. Then in the next case, what I want to have a look at is that we can choose different frequencies to evaluate our pictures. For example, here 17.6 to 18.1 kilohertz, and you can see the very clear picture we saw before. But if we extend this frequency range for our evaluation to, for example, 15 to 20 kilohertz, you can see that there's a lot of additional interference appearing in the acoustic map. So again, our results depend on the evaluated frequency range. And then for the last option in our evaluation, we have a look at the selected dynamic range. And in this case, we use the low frequency source. And as you can see, the dynamic range is 1.3 decibel. That means on this acoustic picture, only the loudest 1.3 decibel points are shown. If we lower or reduce this dynamic range, suddenly the leak due to the hinge disappears. So that's a bummer, so to say. And then when we extend this this dynamic range, it can happen that some new leakages suddenly appear. And in this case, we know that's not a leakage because we weren't able to find it with any other method. We knew, and that's why we concluded that this is just a reflection of some ambient noise, or maybe the noise coming out of this hole. So you see, again, we have to look very closely into the dynamic range. So to conclude, we have demonstrated both the potential but also the challenges of the acoustic method. Our lab results showed that we can detect very complex paths, although of course there is a limit to it. And in the field, we were able to perform several successful trials on real buildings. We were able to cover large areas and large distances, but we also presented quite a lot of typical challenges, especially in the evaluation. And that means right at this moment, the interpretation still requires a lot of experience and also acoustic expertise. And that is why we are, of course, still investigating this method. Right now, our main focus is on suppressing interference signals, increasing automation in the evaluation process, and combining this measurement with thermographic methods. That's it. I would like to give a huge shout out to Björn Schirike and Alexander Janke, first from the DLR and second from GFIE, who held the original presentation at last year's Build Air conference. Thank you all for listening, and I'm happy to answer the question now or maybe later per mail.